Measuring microscopic electrical signals in the real world is difficult because those tiny voltages are constantly swimming in a sea of massive electromagnetic interference. This input separates into two parts: the tiny differential signal, our actual data, and the massive common mode voltage. Our objective is to subtract this common mode wave while keeping the differential data mathematically undisturbed. If a circuit cannot cleanly separate these two voltages, the instrument becomes useless. The background noise will entirely overwhelm the sensor, obscuring the actual data. The most basic approach to this problem is a standard single op-amp differential amplifier. To measure a fragile source signal without drawing current, the circuit requires extremely high input impedance at these two highlighted input resistors. Simultaneously, achieving high differential gain requires an extreme ratio between the feedback and input resistors. This creates a direct conflict. Pushing for high impedance and high gain simultaneously degrades the common mode rejection ratio. Furthermore, even a 1% manufacturing variance between these four resistors triggers massive static offset errors at the output. When you combine that resistor mismatch with the op-amp's inherent offset voltages and offset currents, the total error can compound to over 100%. Extracting the signal requires an architecture that decouples the differential gain from the common mode processing. The two op-amp architecture achieves massive input impedance by feeding signals directly into non-inverting terminals. However, we must test its common mode capacity. The mathematical flaw is the first stage amplifies everything, multiplying both tiny signal and massive noise by the same gain factor. If a massive common mode voltage spike hits, the multiplied noise causes the first stage to hit its physical power ceiling, severely distorting the waveform. This saturation corrupts the data entirely, rendering the high input impedance useless. High input impedance doesn't matter if the architecture cannot survive the baseline environmental noise without clipping. The industry standard architecture is the 3 op-amp instrumentation amplifier. The input stage consists of two non-inverting buffers, A1 and A2, flanking a cross-coupling gain resistor, R1. The output stage is a traditional difference amplifier, A3, which finalizes signal processing. This topology physically divides the labor. Signal intake is separated from the final subtraction process. The signal passes through two intermediate nodes connecting the input buffers to the output stage. Dividing the labor across 3 distinct op-amps creates a mathematical buffer zone, where the delicate signal and the chaotic noise are treated as completely different entities. Returning to the schematic, we apply the superposition theorem. Analyzing input V1 while holding V2 passive tracks the signal through the cross-coupled resistor, giving us the final voltage equation for intermediate node V3. Symmetrical logic yields the equation for node V4. Notice the multiplier attached to the differential input. It is a massive gain factor determined by the resistors, but the multiplier attached to the common mode term is exactly 1. The common mode noise is reproduced at the intermediate nodes, but because of the cross-coupling architecture, it is completely unamplified. We shift our focus to the output stage, A3. The unamplified noise terms from V3 and V4 enter A3 and mathematically cancel each other out to 0 at the final output. There is a manufacturing benefit. If op-amps A1 and A2 are built onto the exact same silicon chip, their inherent offset voltages become nearly identical. Fed into the subtraction stage, these identical offset errors mathematically cancel each other out, eliminating the severe static error that plagued older designs. The 3 op-amp topology mathematically isolates the noise. It allows the entire circuit to simultaneously achieve high gain, high impedance, and high common mode rejection. Even with this mathematical precision, instrumentation amplifiers face physical hardware limits. Standard op-amps are bound by their direct current power supply rails. Any common mode voltage exceeding roughly 15 volts will physically destroy the silicon. In extreme environments, such as a medical defibrillator or industrial motor drive, common mode noise can spike to 2,000 volts. At kilovolt levels, a continuous electrical wire will transmit that massive surge directly into the processing equipment, causing catastrophic failure. The architectural solution for extreme environments is the isolation amplifier. To sever the continuous electrical wire, this circuit uses a galvanic barrier. The signal is converted and transmitted across a physical gap using optical light, magnetic fields, or capacitive coupling. This topology creates two completely separate grounds, an input ground exposed to the high voltage and a safe, isolated output ground. Hardware in this environment is judged by its isolation mode rejection ratio, or IMRR, which measures how well that physical barrier repels kilovolts of potential difference. Signal integrity requires a dual approach. Mathematical architecture filters out normal interference, while brute physical topology survives the extremes of the real world.